Alright, here we go. Let's implement the training operations. So we're going to make a series of functions before we get to that final loss function, because indeed the formula is quite complex, so we're going to split that into several steps. And the first thing we're going to do here is just get a special number, which results from a complex operation, but that special number is something around 0.92 or 0.94. We'll check that right away. And this special number is just the log of the square root of 2 times pi. So we're going to put that number into a variable, which we're going to call log sqrt 2 pi, which, as we've just said, is going to be equal to the following formula. The log, which I'm getting thanks to numpy log, that's a function by numpy, of the square root, which again I'm going to get thanks to numpy, np.sqrt, another function by numpy, of, as we said, 2.0 times pi, which again we're going to get through numpy with np.pi. Here we go. And that's just the number I would like to get, which is of course part of the loss function that we're going to use to train our MDN RNN. And let's just check that if my memories are correct. If we execute this, here we go, we have our log square root 2 pi, and now let's just select this, let's execute again, and here we go, yes, 0.92, right? So that's a special number, which is part of the loss function. And speaking of the loss function, well, we're not ready to get it yet. I would like to do an intermediary step, which is to compute another formula, which will include that log squared 2 pi, and which we're going to include inside a new function, you know, like this one here, which we're going to call def tf log normal. All right, so we're making it because it is not part of the TensorFlow tools right now for the TensorFlow version we're using, and therefore we have to make this formula from scratch ourselves. And so this function is going to take 3 arguments. The first one is the target, which we'll call here just as an argument y, but then which will be later on the target in the MDN training. Then the second one is one of the parameters of the MDN, which is going to be the mean. So we're just going to input mean here as the name of the argument. And then the third one is going to be another of the MDN coefficients or parameters, which will be the log std. And actually, we will keep that name for the argument, log std. All right, and now inside the function, we're just simply going to include that major part of that loss function, but which will still not be the final loss function, but it will be indeed the big part of the computation, which is like a log normal distribution. And so that big operation, well, let's return it directly. It is going to be minus 0.5 times a fraction, which will be first at the numerator y, the target, minus the mean, divided by the exponential, which we will get from TensorFlow, so tf.exp, the exponential of, well, that MDN parameter, the log std. All right, then we're going to take the square of all this, and to do this, we just need to add here a double star, then 2. And then finally, we have to subtract the log std and subtract again, well, that special number which we've introduced before, the log square root of 2 pi. All right, so pasting that here, and here we go. That's the major part of the loss computation, which we're going to include now in a final function, which will be that loss function itself. And so I'm introducing a new function here, def, and we're going to call that loss get loss function, get loss func, which will take 4 arguments. First one will be, of course, one MDN parameter which we haven't used yet in this big operation, which is of course the outlog mix, the mixing coefficients. And so that's our first argument here, the log mix. So this is just the name of the argument, but then of course we'll input the real variable for that, outlog mix. Then the next 2 parameters are going to be the other 2 MDN parameters, which are the mean and the log std. And then finally, well, y here in the tf log normal function that we've made ourselves, which is the target. So we're simply going to call it y now, but then we'll introduce a new variable for that target. And so here we go for the final round of that loss function. So I can already start to tell you what is going to be the final operation of that loss function. Well, it is going to be minus the mean, which we're going to compute thanks to math reduce mean, which I've prepared for you again. Math reduce mean minus the mean of the log of the sum of the exponentials of the log mix variable plus that operation here, right? The elements resulting from the operations here. So no worries, we will write that in several steps. So the first step is actually to get this outcome here resulting from this formula. And we're going to put that outcome in a local variable, which I'm going to call v. So v equals, then we're going to call that function tf log normal, and actually also its arguments, because we used the same names for the arguments of that get loss function. So copying this and pasting that here. But then remember, I told you that the elements of which we're taking the log of the sum of the exponentials are actually that plus the log mix, right? These are going to be the elements inside that log sum exp, right? And therefore now we're ready to take again that tf reduce log sum x function. So taking that again, and just below, well, we're still going to call that v because we're just updating this local variable. And so here we go. I'm pasting again that tf reduce log sum exp, taking as arguments the same one. First, the elements of which we're computing the log of the sum of the exponentials, which we called v, exactly what we had here. Those are the elements inside this big log of the sum of the exponentials operation. Then, remember, we have to specify the axis, and as usual, we are making this operation along the observations, the rows, so the horizontal axis which has index 1. And then, remember again, since we're using the alias on a deprecated version, well, we have to take again that argument and not keep its default value of none, but true. So copying this again and pasting that here. All right, so almost there. We have one final step before we get the final outcome of the loss function, which is, remember, to take the mean of all this, or more specifically, minus the mean of all this. And therefore, since we're ready to return the final outcome, well, we can end this function with a return, and then, as we said, it's going to be minus the mean of what we've just computed, which we're going to get thanks to this math reduce mean function, or more precisely, the alias tf.reduceMean. Right, so I'm taking this and pasting the final outcome here, the mean of v. And congratulations, you made this pretty complex loss function, which indeed we had to compute in several intermediary steps, right? It's easier to do it this way, it's more clear and not too overwhelming. All right, and now that we have our function ready, let's get the final loss. And to do this, we're going to have to call that getLoss function with the right argument. So we already have 3 arguments. We have the log mix, which we've prepared here, out log mix, as the result of the getMDNCoef function. Then we also have the mean, again, still as another output resulting from the getMDNCoef function, out mean. We also have the log std, again, the third element, the third MDN parameter resulting from the split of the output, but we don't have yet y, which is, I remind, the target. And so that's exactly what we're going to get right now. We're going to get that target, which we're going to call inside a new variable, flat target data. All right. And to get the target, well, we're going to have to do another reshape. Remember that we already prepared something for the target. It was, I remind, this output x, which we've prepared thanks to a TensorFlow placeholder. And so we're going to take that placeholder again, output x, and even we're going to take self.output x, because this flat target data, meaning this y in the getLoss function, is going to be that output x, but just a little bit reshaped. And the way it's going to be reshaped is by doing the following. first we're going to call, of course, the reshape function by TensorFlow, tf.reshape, inside which we're going to do something different this time. The first argument is going to be, of course, what we want to reshape, which is this output x, self.output x, that placeholder we prepared for the target. And then, exactly as what we did here, we're going to reshape that with the following format, with that -1, which will flatten some dimensions. But here, it's not going to be, of course, hps.rnn side. It's going to be a full flattening because we're just going to input 1. And I'm going to show you the before and after the reshape. So I'm taking this, pasting here inside the reshape function as the second argument. And here, as we said, it's going to be a simple 1 for, how we group the elements resulting from that reshape. And so now let's see what the new target becomes. So first we're going to execute this, but because of the self, I can execute that here to see the shape because it is inside a function. So that's why, I prepared this RNN values Python implementation, which contains all the values of the MDN RNN. And so here we go. Now I can select this, just the output X, and execute. And here we go, we have the shape. So it is a 3D tensor. So that's the original shape of the target we prepared before. It is a 3D tensor of, remember, 100 samples in this first dimension of the batch, 1000 frames, which are the successive frames to learn the time-related dependencies happening in the game. And more specifically, these are the reconstructed frames resulting from the VAE. And then 32 for, remember, the output sec width. And so that's the original shape. And now what happens after the reshape? So we have to scroll down a bit and find that flat target data. Here it is. So I'm going to first execute this. Here we go. And now I'm going to execute only this flat target data. And now let's see the new shape. It is going to be, as we've just said, a full flattening of all the elements one by one, with therefore 3,200,000 rows. So that results indeed from the multiplication of 32 times 1000 times 100, because it was indeed a full flattening along one dimension, one single dimension, and of course one column, because indeed all the elements in the 32 elements of the output in all the 1000 frames, reconstructed frames of the sequence lengths of all the 100 samples of the batch were grouped one by one and flattened into this one single one-dimensional vector, which can be seen as a vertical vector. Alright, so once again, you clearly see what we're doing here with all the reshapes. And now that the reshape is done, we can move on to the next step here, which is to finally call that getLoss function, because indeed, now we have all the arguments ready to be input inside this getLoss function that is going to give us the final loss. Alright, so, well, here we go. Let's copy this, and we'll just replace the right names of the arguments. So, since this getLoss function returns the final loss, well, we have to introduce a new variable which will contain that final loss, and which therefore we'll call lossFunc, and that variable is going to be the result of the getLoss function, which is going to take as arguments, of course, the parameters of the MDN plus that target which we've prepared here. So let's put the right names of these variables, which we've already prepared. The first one, logmix, we call that actually out logmix. Then the second one, the mean of the MDN parameters, we call that the out mean. And then again, the log std, we call that out log std. And y, the target, we just call that flat target data. So I'm copying this, pasting that here, and here we go. Of course, let's remove the colon. Perfect. So that gives us the loss function, but now to get exactly the loss, which is also called cost, well, we have to more precisely get the mean of that outcome, that outcome returned by the getLossFunc function. And so to finish this, well, to finish the big first part of the training operations, because then we'll have to introduce our optimizer, well, we're going to introduce a new variable which will be exactly the final loss error, or also called cost, and which, as we said, is going to be the mean, which again we get by TensorFlow, right? TensorFlow dot reduce mean of that loss func variable, which is the result of that get loss func function. All right, and now we can move on to the final part of the training operations with, the introduction of the learning rate, the optimizer, and then of course we're going to apply the gradients from the optimizer exactly as what we did for the VAE. But of course now let's take a little break and let's do that final part of the training operations in the next tutorial. And so until then, enjoy AI.